तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
This is the last lecture on the topic of MOS junction or capacitor. Let us quickly summarize what we achieved in the previous lecture. In the previous lecture, we explained the low frequency and high frequency CV characteristics. Then we did some calculations to show how we can get the critical capacitance and voltage values on the measured capacitance voltage curve. This was our measured capacitance voltage curve. Our calculations, starting from the doping level of the substrate, the oxide thickness, and the fact that the gate was made of aluminum metal, gave us the following characteristics. So the critical values of the minimum capacitance was 0.7, this is normalized capacitance. So minimum normalized capacitance was 0.7, threshold voltage was 1 volt. This 1 volt threshold voltage was actually obtained directly from the measured characteristics, whereas this 0.7 value was estimated. And then we also estimated the flat band voltage. Now let us look at this flat band voltage in a little bit more detail. This value 0.7 is very close to 0.685 that we observe on the CV characteristics. So if on the CV characteristics, if you see, this minimum value here is little less than 0.7, but quite close to 0.7. However, the flat band voltage is minus 2.98 as calculated by us, which is very different from what we have been showing here. So on the measured curve, this appears to be the kind of approximate flat band point, because beyond this the curve has started dropping, whereas according to our calculation the picture is something like this. So flat band voltage is about minus 3. Now how do we explain this? This is an important point that we have to understand. The fact is that what we have derived is an approximate CV curve which has 3 segments. Suppose this is the flat band point and this is the threshold point. The curve C versus V has 3 segments. One is a constant segment, then you have a segment that is a kind of square law, which goes like this. It is a quadratic equation for capacitance versus voltage, which is cut off. This segment is cut off at the threshold voltage point. For high frequency curve and for high frequency capacitance, you have another constant segment here. For low frequency capacitance, it goes up to this value, which is C0. So this curve is actually an approximate curve. You cannot have a sharp transition like this at this point at the flat band voltage. In fact, your actual curve, if you make rigorous calculations, would turn out to be something like this. Okay, so here at the flat band point, the capacitance is not exactly C0, In fact, it can be shown to be this capacitance C flat band can be shown to be equal to a series combination of C naught and a semiconductor capacitance that is given by C naught into Cs by C naught plus Cs, where Cs is equal to epsilon S by Ld, where Ld is called the Debye length, which we have talked about earlier in the context of PN junction. Okay, so at the flat band point the picture is something like this. This is the oxide layer, and you have a small space charge layer like this whose length is equal to Debye length. So this is the flat band voltage which you are applying. So the capacitance therefore is series combination of the oxide capacitance which comes here and the semiconductor capacitance which comes there. Okay, so these two capacitances. So that is one of the reasons why if you see the flat band point on the CV curve, you find the capacitance has dropped below the value C naught, or normalized capacitance has dropped below 1. This is one of the reasons why again the flat band point is somewhat difficult to locate. Okay. Now apart from that, there are also other deviations which we have not considered. Okay. So the measured characteristics will also have effects of the interface charges QIT. Okay. And the interface charge, the behavior is somewhat more complex as a function of voltage. Unlike the fixed charge, the interface charge QIT can change with voltage, and therefore there will be a stretch out effect of this curve. In other words, the curve will not be this, but it would be something like this. Okay. So this is another reason why the flat band point will deviate from the calculated value to more negative values for a p-type substrate. So this explains why, although the calculated flat band point is somewhere here as shown on this slide at -3, the actual flat band point could be away somewhere here. In fact, this point has to be located by some involved calculations or argumentation. So we will not discuss this point related to flat band voltage further. Okay, we have explained what are the kind of deviations of the measured characteristics from the calculated characteristics. Now we come to the final topic of the MOS junction or capacitor, and that is the body effect, where we come to the discussion of the 3-terminal MOS junction or capacitor. So this body effect is seen when you have a capacitor like this, and we connect another contact here. For the purpose of simplicity, we will assume that this contact is really very small, okay, and this contact is made of N plus. This contact enables you to establish a connection with the inversion layer here, which appears if you apply a voltage more than the threshold voltage. So here this voltage is more than threshold voltage. So as a result, you have created an inversion layer here of electrons. Of course, you have the depletion layer already. you are using this contact to connect to this inversion layer of electrons. That is why the contact is N plus. Now, what we want to study is what will happen if you change the potential of the inversion layer of electrons by applying a voltage to the N plus contact. So here we apply a voltage with respect to the bulk. So this bulk point is being taken as a common for both gate as well as for this particular contact. We want to see if you vary this voltage, what effect will it have on the charge here. That is why this is called a 3-terminal MOS capacitor now. You have this terminal and this is the third terminal. The question is, what do we call this contact? We will call this contact as the source. So this is the gate and this is the source. And this contact is called the bulk. This is called the source because it can be shown that if you make small changes in the voltages, then at high frequencies, even at high frequencies, you will be able to get the layer of electrons changed in response to the change in voltage because of this contact providing electrons to this layer. So in a 2-terminal MOS capacitor where this N plus contact is not there, as we have discussed earlier, if you make a change in the voltage at very high frequencies, then the change in the charge occurs at the edge of the depletion layer. That is why the high frequency capacitance is constant at a minimum value, whereas the low frequency capacitance goes up to the oxide capacitance. So unlike that situation, in a 3-terminal MOS capacitor, once you provide the N plus contact, even if you make changes in the voltage at high frequency, changes in the gate voltage at very high frequencies, you can have this inversion layer responding to the change because this N plus region has a large supply of electrons and it can provide electrons as fast as this layer needs. That is why this contact is referred to as the source, because it can source the electrons required for inversion layer changes. Now since this is called the source and now there are two voltages here, we should distinguish between the two voltages. So what we will do is we will call this as Vs, that is the source voltage, and we will call this as the Vg, that is the gate voltage. We didn't have this problem in a 2-terminal capacitor because there was only one power supply. Now as we will note, the body effect is actually a change in the threshold voltage because of the power supply Vs. That being the case, what we will do is we will define the threshold voltage for 0 source voltage, that is the threshold voltage that we have estimated in the last class, as Vt0. So Vt0 is the threshold voltage of the device corresponding to Vs equal to 0. So when Vs is equal to 0, this contact is shorted to the bulk, and it can be shown that whether the contact is shorted to the bulk or whether it is kept open circuit, it really has no effect on the inversion layer, and therefore the device behavior when this N plus contact is either open circuited or short circuited to the bulk is the same as the device behavior of a 2-terminal MOS capacitor. So the threshold voltage of that 2-terminal MOS capacitor is Vt0. Now to understand the effect of this Vs, on the inversion layer, what we should do is we should start with a gate voltage which is very large, so that it is more than the threshold voltage corresponding to Vs equal to 0. So in other words, what we are doing is we have the N plus contact, but we don't apply this Vs, so we blank out this Vs, there is no Vs, and we apply a gate voltage which is much more than the threshold voltage corresponding to the condition when there was no Vs. So that ensures that you have a sufficiently large inversion layer charge. Now you superimpose a Vs here, you connect a Vs between the source and the bulk, and you start increasing this Vs from very small values, and you see the effect. Now one doubt will arise, what should be the polarity of Vs? Should it be positive or should it be negative? Now we have already explained why this contact is N plus, okay, because the purpose of this contact is to provide a connection to this inversion layer, and also the contact should not provide this particular block should not provide any contact to P, we only want to contact the N plus. So the only way you can achieve this is to put an N plus region here. For example, if you put a P region, it cannot make contact to the inversion layer, which is large number of electrons. There will be a junction between the inversion layer and the P region here. So you can only have N plus region there. Now the question is, what is the polarity of Vs? Now note that if the N plus contact is made negative with respect to bulk, then this P N plus junction will get forward biased, and when there is a forward bias across the junction, you know that a large current flows. So what will happen is that if your N plus contact is made of negative polarity with respect to the bulk P type region or substrate P type region, then a large current will flow through this contact. Also you cannot vary the voltage over a very wide range, because you know that beyond 0.7 volts currents start shooting rapidly in the forward bias direction, and therefore if you increase the voltage too much, the current will be very large, power dissipation will be large, and the device may burn out. So if you apply a forward bias here, there are two problems. One is that there is a large forward current in the device which you cannot control by the gate, and also you cannot have a very wide variation in the voltage to control the N plus region, to control the inversion layer charge. Therefore we are only allowed a positive voltage to N plus contact with respect to P. In other words, the P N plus junction should only be reverse biased. Okay, now we start increasing Vs. What is the effect? To understand the effect of Vs on inversion layer, it is useful to regard this particular region of the MOS capacitor next to the interface as an induced NP junction, okay. Induced N plus P junction. So this induced N plus P junction is between inversion layer and P substrate. So inversion layer has majority electrons and P has majority holes, therefore there is a PN junction here, and we call it induced junction because this has been induced by application of a gate voltage beyond the threshold voltage. Now once we recognize that this is an induced N plus P junction, we can easily see what is the effect of applying a reverse bias Vs on this junction. Note that this voltage is getting transferred to this inversion layer. So the situation for this particular space charge region here can be shown as follows. So this is the inversion layer, N plus, this is P, this is the depletion layer, and the voltage across this is, you are applying a voltage which is equal to Vs. So what is the effect of this Vs? Evidently the effect of the Vs is to expand the depletion layer, because this is a reverse bias across this junction. So if for Vs equal to 0, your depletion layer was something like this. So this is for Vs equal to 0. So this was the depletion layer when you didn't really connect the power supply Vs to the N plus contact. So when you connected this Vs, then the depletion layer obviously will increase. So in other words, this results in increase in the depletion charge. Okay, so as Vs increases, you have increase in the depletion layer thickness. So this is XD, depletion layer thickness, which means you have increase in the magnitude of QD, and it also means you have increase in the potential drop across the semiconductor. Okay. Now recall that whatever gate voltage you apply, part of it drops across the oxide and remaining part drops across the semiconductor. Now what we will do is, when we are discussing the body effect, we will start with an ideal MOS capacitor, and then you can always incorporate the effect of non-ideality by incorporating the non-zero flat band voltage. So if you assume an ideal MOS capacitor, then you know that we can write Vg is equal to psi ox plus psi s. So potential drop across the oxide and potential drop across semiconductor. This psi s is nothing but the potential drop here in the induced N plus P junction, or if you look at it in terms of this MOS capacitor, this is psi ox and this is psi s. So clearly now what this diagram shows is that psi s increases, your XD is increasing, depletion charge is increasing, and so psi s is also increasing. So Vs increasing implies result of Vs increase is XD increasing, magnitude of QD increasing, and psi s also increasing. Now if psi s increases but your gate voltage has been maintained constant, please recall this here. We have applied a gate voltage which is more than threshold voltage corresponding to 0 Vs, but we are not changing the Vg when we change Vs. That is how you discuss the effect of any input parameter. If you have a number of parameters in a given situation and you want to see the effect of any one parameter, other parameters should be maintained constant. So here you are maintaining Vg constant, and as you change Vs, your psi s is increasing. Now this means that from here, if psi s increases, Vg is constant, psi ox decreases. So psi ox falls since Vg is constant. Now what is the effect of psi ox falling? Recall that the potential drop across the oxide is equal to the total charge in silicon divided by the oxide capacitance. Okay, this is from a simple parallel plate capacitor physics, we have discussed this point. So Qs is the total charge in silicon, including the inversion charge and the depletion charge. This Ψox is Qs by Cox, of course with a negative polarity, because when you apply a positive voltage to the gate, charge here is negative. So when you write here Ψox is equal to minus Qs by Cox, and Qs is Qi plus Qd, that is inversion charge plus depletion charge, then what follows from this condition is that Qs falls. If Ψox is reduced, then it obviously means Qs is reduced. So another effect of Vs is Qs falling. So please note that we are proceeding in this order, okay, in a logical fashion. So first you start with increase in the depletion width, and then logically this means Qd increases in magnitude. This also means Ψs increases in magnitude, and since Vg is constant, it means Ψox decreases in magnitude, and Ψox decreasing in magnitude means Qs decreasing in magnitude. Now Qd magnitude is increasing and Qs is decreasing. Look at this equation. If Qs decreases in magnitude and Qd increases, then clearly Qi is going to fall, because Qi is difference of Qs and Qd. So the result is, now here we should put a modulus because Qs is negative in magnitude, in polarity. So magnitude of Qs decreases, so Qi magnitude decreases. Since Qi is equal to Qs minus Qd. Now this is the important result. A consequence of increase in Vs. So what we derive from here is that the effect of increase in Vs is decrease in the inversion charge, but increase in the depletion charge. Okay. So here, that means in this junction, as this depletion width expands, the amount of electrons in this n plus region will go on decreasing. Now therefore it appears quite logical that for some value of Vs, this inversion charge which is decreasing can become equal to 0. Okay. Now if inversion charge becomes 0, obviously the device has reached a threshold condition, okay, because threshold condition corresponds to inversion charge just starting to increase if you are increasing the gate voltage. On the other hand, if you are decreasing the gate voltage, it is a point when the inversion charge just goes to 0. Now in this case we are not changing the gate voltage, but we are changing the source voltage, but that does not matter, right. What it means is, as you change the Vs, at some point the inversion charge is coming to 0, and therefore this is a threshold point. So what this means is that we started with a gate voltage which is more than threshold voltage at Vs corresponding to 0, but maintaining Vg at this value, as you increased Vs, you came to a condition when the Qi became 0 for some Vs, which means now this gate voltage which was more than Vt0 is actually a threshold condition for some value of Vs, non-zero value of Vs. Let us see what is this value of Vs, okay, at which the Qi will become 0. So for this purpose we should write an expression for Qi as a function of the various voltages. This can be done easily as follows. You write Qi is equal to Qs minus Qd, where Qs is psi ox into C naught with a negative sign. Okay, this follows from this formula. Qs is psi naught x into this is actually C naught. We have been using the symbol C naught instead of C ox. So minus psi ox C naught minus Qd. Psi ox is nothing but Vg minus psi s Now, what is the value of psi s? Psi s is equal to the potential drop across the n plus p junction, okay, the internal potential drop. The external applied reverse bias is Vs, but when Vs is equal to 0, you still have a depletion layer, because you know that there is a psi s when you create an inversion layer, and that psi s is equal to phi t or twice phi f. Okay, so when an inversion layer is created, obviously there is a potential drop in silicon, otherwise you cannot create the inversion layer, and that potential drop is equal to phi t or twice phi f. So when Vs is equal to 0, psi s is twice phi f or phi t. So for any non-zero Vs reverse bias, your potential drop across the induced NP junction from the PN junction theory will be the built-in potential plus the reverse bias. Here the phi t is like the built-in potential for this n plus p junction. Okay. So we can write psi s is equal to phi t plus Vs. Now once we know this psi s, we can also write an expression for Qd in terms of psi s. So you recall that when the capacitor, it was an ideal capacitor under inversion, then we wrote down the expression for Qd as square root of 2q Na epsilon s into phi t. This was when it was a two terminal capacitor and it was in inversion. Now all that you need to do is you replace phi t by phi t plus Vs, because this is the new value of psi s. This phi t is nothing but actually psi s. Of course you should have a negative sign here, because the charge is negative in polarity. So now we can substitute these two terms here, and we can get an expression for inversion charge as Qi is equal to minus Vg minus phi t minus Vs minus into C naught minus Qd. Qd is minus of this quantity, so therefore you get plus square root of 2q Na epsilon s into phi t plus Vs. Now clearly from here you can slightly write this equation, reorganize the terms, and you can write it as follows. You can write this as minus of Vg minus Vt into C naught. That is when you can write it as in this form, and you can recognize that the Vt here would be, from this equation you can see that this Vt is equal to square root 2q epsilon s Na into phi t plus Vs upon C naught plus phi t plus Vs, where this is the so called potential drop in the oxide and this quantity is the potential drop in silicon. Okay, that is the gate voltage Vt. Now what is the idea in writing it in this form? You recognize that Qi is 0 when Vg is equal to Vt. So this means this is your new threshold voltage. Okay, as a function of Vs. So we can check this particular expression by considering a limiting case. This expression must reduce to the expression we had for threshold voltage for Vs equal to 0 if you substitute Vs equal to 0. Now you see here, if you substitute Vs equal to 0, you end up getting that expression which we derived for ideal MOS capacitor earlier. So this is the body effect, the increase in threshold voltage with Vs. Clearly the right hand side increases as you increase the Vs. So we can write this threshold voltage also in terms of Vt0 to clearly show the increase in threshold voltage as compared to the condition Vs equal to 0. So this is the Vt for an ideal MOS capacitor including body effect, and this is Vt0. So we can write Vt minus Vt0, normally referred to as delta Vt. So this delta Vt is equal to, this is actually denoting the body effect. You subtract this equation from the equation in which Vs was 0. Clearly therefore you will get square root 2q epsilon s Na into phi t plus Vs So we can take this actually out. So this by C naught into square root phi t plus Vs minus square root phi t plus Vs. This is the delta Vt. We should emphasize that we are using the bulk terminal as a common terminal for applying Vs and Vg. We will see later that this value gets modified if you use the source as a common terminal and apply gate voltage with respect to source and bulk voltage with respect to source. We will find that actually this term Vs will drop out. This we will see when we take up the MOSFET. Okay. Now this term here is normally given the symbol gamma. Okay. So normally delta Vt is written as gamma times this, where this gamma is square root 2q epsilon s Na upon C naught. So this is your body effect. Now we had explained all this assuming an ideal MOS capacitor. So which means the flat band voltage was assumed to be 0. If the flat band voltage is not 0, we can now include its effect very easily. All that we need to do is we should replace Vt by Vt minus Vfb. Okay. Delta Vt will not be affected because when you subtract Vt0 from Vt, both will have a flat band voltage term and that term will get cancelled. So including Vt, including flat band voltage, I am sorry, you can write the threshold voltage as flat band voltage plus Vs plus phi t plus gamma into square root of phi t plus Vs. So this is the threshold voltage of a 3-terminal MOS capacitor. Okay. In order that we understand the body effect very clearly, we can discuss the same thing that we were elaborating upon so far in a slightly different way. So far we assumed Vg to be constant at a value greater than threshold voltage for Vs equal to 0, and then we increase the Vs to see what is happening, and we explained that the inversion charge is going to reduce. Let us try to see what will happen if you keep Vs constant and you increase Vg from 0. So instead of keeping Vg constant and increasing Vs from 0, we keep Vs constant and increase Vg from 0. What is going to happen? So this is now variable and this is constant. What is the effect? Now the effect will be that your depletion region will start increasing from 0. It will continue to increase until you have your gate voltage equal to the threshold voltage as explained earlier and as written in this expression. So until you reach this value of Vt, your depletion width will go on expanding. So this is what is happening. So your depletion region first is here for small Vg, then it expands further, you increase your Vg, you increase your Vg further, it expands. Now what is important is this will continue to expand until you reach Vg equal to the Vt taking into account the effect of Vs. So that will be a larger Vt than the Vt that you had for Vs equal to 0. So this will continue until that point, and then an inversion layer will appear here. So when the inversion layer appears, that is when the threshold is reached, then your voltage drop here will be phi t plus Vs. So the depletion region keeps on expanding until the voltage drop in silicon reaches phi t plus Vs, and thereafter an inversion layer develops. So this can also be shown using a space charge diagram. So we are drawing this space charge conditions when Vs is constant and Vg is varying. So here what is happening is you have a depletion layer like this to start with for one value of Vg, you go on increasing your Vg, you have depletion region expanding until you come to threshold. Beyond threshold, the depletion region stops expanding and you have the inversion charge. So let us call this 1, this is 2, this is 3, and this is also 4, because your depletion region almost stops expanding beyond threshold. Okay, so 4 is into threshold. So Vg 3 is equal to Vt including the body effect, and Vg4 is greater than Vt. So if you apply even higher voltage, this inversion charge will go on increasing. Exactly similar diagram if you would like to draw for the condition Vg is constant and Vs varying. This is what we had discussed earlier. Okay, so to complete the explanation we will draw that diagram also. That diagram would look something like this. So first you are starting with the condition Vs equal to 0. So therefore, supposing your depletion width was this much, the device was inverted and therefore you had this charge. So this is the depletion width in threshold, beyond threshold in inversion, okay, because this corresponds to Vs equal to 0, and this is also 1. So 1 is Vs equal to 0. Now you are going on increasing your Vs, so what happens is this is expanding. So this is 2, and inversion charge is decreasing simultaneously. And for 3, which corresponds to threshold, you reach the same depletion layer here that you had, okay, assuming that this Vs is the same as the Vs corresponding to this. So you started with a smaller depletion layer thickness than this, because one corresponds to Vs equal to 0, whereas this threshold condition corresponds to some value of Vs. So here when you keep Vg constant and you go on increasing your Vs, your depletion region expands and inversion charge goes on falling. For 3, inversion charge is 0. For 3, inversion charge is equal to 0. So we are not showing 3 here, and this is a threshold condition. So in summary, that is the body effect. Now many times the body effect is derived with the help of energy band diagrams. We have avoided the use of energy band diagrams because the explanation in such a manner is simpler. So one can also use the energy band diagram and one can get the same information as well as some more additional information. Now let us do a simple numerical example to illustrate the body effect. So this is the example. Calculate the increase in threshold voltage of the 2-terminal MOS capacitor considered in the earlier solved examples when an N plus source biased at 5 volt with respect to the P substrate is connected to the inversion layer of the capacitor. So this is the diagram. This is the MOS capacitor, P type substrate, doping level 1.45 into 10 power 16 per centimeter cube, and oxide thickness of 0.2 micrometer. You are connecting an N plus substrate here, N plus source I am sorry, to the inversion layer which may form at the interface, and you are applying 5 volts. You want to know, because of the connection of this particular power supply and source, how will the threshold voltage increase? So threshold voltage is the voltage you must apply here so that you get an inversion layer. Of course, when you have an inversion layer, you will also have a depletion layer. Now let us look at the equation that we have derived for this particular purpose. This is the expression for threshold voltage, and this is expression for change in threshold voltage. So you find in the expression for change in threshold voltage, we have only the source voltage Vs and the voltage drop in the semiconductor at inversion when the source voltage is 0, that is phi t, and the parameter gamma, which contains the doping level of the substrate and the oxide capacitance. So you do not have the flat band voltage term coming in here. This means that for an ideal capacitor and for a real capacitor, the change in the threshold voltage with the source bias or the body effect is same. Now let us substitute the values here. So gamma is equal to square root of 2 into 1.6, we collect the powers separately, 10 power minus 19 into 1.45 10 power 16 into 10 power minus 12 divided by 17.7 into 10 power minus 9 farad per centimeter. So you check that dimensionally this is correct. Okay, I am not putting the dimensions here, but you must put the dimensions and check. So when you solve this, you will get the result as 0.385. Now what will be the unit of this body effect parameter? Please note from here that the unit of gamma into this quantity should be volts. Okay, that is what is left hand side, that is also the other term here. So since this is root volts, obviously gamma should also be square root volts. So that is the body effect parameter gamma. Now you substitute this gamma here and you will get delta Vt equal to 0.385 into square root of phi t was about 0.72 plus Vs is 5 minus square root of 0.72 plus 5, that is the Vs here, and this will turn out to be 5.594 volts. So that is the increase in threshold voltage. The threshold voltage with respect to bulk, I must emphasize this, threshold voltage with respect to bulk has increased by 5.594 volts. So that is a new threshold voltage. Okay. Now with this we come to the end of the discussion on body effect. I will be happy to answer any doubts if you have.
Sir, I have a question regarding the work function difference 5 ms. You have explained how it is estimated for aluminum gate. Will you please tell us how does one estimate it for a polysilicon gate?
The procedure for estimating 5 ms for a polysilicon gate is very similar to that for a metal. Look at this energy band diagram. This is p-type substrate. On the left hand side you have the polysilicon gate. Now the polysilicon gate is either heavily doped n-type or heavily doped p-type. Now please note that the polysilicon gate is always heavily doped because its resistivity should be low. It should act like a conductor, like a metal. So unless you dope it heavily, you will not get this low resistivity. Now generally, if the polysilicon gate is heavily n-type, then the Fermi level is assumed to coincide with the conduction bandage. So EFN is here. On the other hand, if it is heavily doped p-type, the Fermi level is assumed to be at the valence bandage. Now once you know the location of the Fermi level, you can easily determine the phi ms. For example, for n-type polysilicon gate and p-type substrate, the phi ms is this much in magnitude. Okay, so you can write the phi ms as, for n poly, phi ms is equal to this phi f and plus this half of the energy gap, that is 0.55 volts. So phi f plus 0.55. Now phi m is above phi s, EF in the poly is above EF in the semiconductor. So phi m, which is this difference, is less than phi s, which is the difference between E0 and EF. So therefore this is negative in polarity. So we are assuming a P substrate. Similarly, if you have P poly and P substrate, then from here it is clear that this is your Fermi level difference, this and this. Now here your phi m is more than phi s. So this difference is 0.55, that is half of energy gap, minus phi f. So phi ms is equal to 0.55 minus phi f. So I leave it as an exercise to you to find out what is the phi ms if you have an n-type substrate and n-type poly and p-type poly. Now let us see the next question.
Sir, I have a question regarding the small signal capacitance in depletion region. I had some difficulty in understanding why this capacitance is regarded as a series combination of oxide capacitance and depletion layer capacitance. Can you throw some more light on this topic?
Okay, let us understand your question with the help of this diagram. This is the incremental charge picture. That is, you have a MOS capacitor which is operating in depletion layer, depletion region. So this is a depletion layer. The voltage applied is V. You make an incremental change in voltage, and as a result you get a change in the charge. This is the change in the charge picture for increment delta V, that is shown here. Now this is the picture relevant to the small signal capacitance. You want to know why a charge here at the gate and a compensating charge at the edge of the depletion layer, this kind of a picture results in a capacitance of this MOS capacitor, which is a series combination of the oxide capacitance and the depletion layer capacitance. You want to understand how this is possible? A very simple way of explaining this is as follows. Supposing you introduce at the interface a negative charge equal to the positive charge here, okay, and you also superimpose on this negative charge a positive charge which is equal to the magnitude of this negative charge, okay. Now these two charges are equal, the positive charge here and negative charge here are equal, therefore these two are equal, therefore in effect we have not introduced any charge, okay, because this plus this is 0. But now supposing you pair up these two charges, they amount to a capacitance equal to the oxide capacitance here, C0. Then you pair up these two charges, they amount to a capacitance here. This is the semiconductor or depletion region capacitance. Therefore, the capacitance of the MOS capacitor in depletion is a series combination of these two, between this point and this point, which is the same as this point. Now with this we have come to the end of this discussion on MOS capacitor. Let us quickly summarize what we have achieved in the last few lectures. First we discussed the structure and fabrication of the MOS capacitor. Then we considered its DC characteristics, charge versus voltage, wherein we defined an ideal MOS capacitor, and then we showed what is the meaning of a non-ideal MOS capacitor. We considered the accumulation, depletion and inversion regions of operation. We defined the threshold voltage and flat band voltage. We also drew the energy band diagram because we showed that if you want to understand the work function difference contribution to the flat band voltage, you have to understand the energy band diagram. The work function difference is nothing but a built-in voltage, okay, of the MOS junction. Then by differentiating the charge versus voltage or QV characteristics, we obtained the low frequency CV characteristics. Then we explained why the high frequency CV characteristics are a little bit different than low frequency. More specifically, under high frequencies the capacitance in inversion saturates to the value which the capacitance value of the capacitance at threshold. Then finally we considered the body effect, where we saw the effect of introducing a third terminal which makes contact with the inversion layer and biasing this third terminal with respect to the substrate. In the next lecture we will start the discussion of the MOS field effect transistor.